Hello everyone, and welcome back to the series on multivariable calculus. Today we're going to be continuing our journey through the realm of multiple integration and discuss a very important mechanism known as the Jacobian matrix. So last time we were going over how to actually calculate multiple integrals, in particular in the rectangular coordinate system. And what do we mean by rectangular coordinate system? The units or the domain that we were working in is x comma y. So pretty much we have a small differential in the x direction, and we had a small differential in the y direction for which span the area of a rectangle. And then fxy obviously represented the height of the associated rectangular prism for which we were using to approximate the double integral under a surface, which geometrically could be viewed as a volume over some domain D. Now, it's very important to note that some domains D are better approximated or represented with other geometries. For example, if I ask you, take this region and approximate it with some shapes, you'll probably be like, oh, I'd probably use rectangles, I'd probably use that rectangle, and then have that rectangle there. But if I say, how would you approximate this region, you're probably like, oh, I can obviously use a sequence of rectangles if I want, but it's possible that I need infinitely many rectangles to cover the entire region. Why not just use just one circle and get the job done with one geometry? So that's pretty much what's going to motivate this existence of this thing called a Jacobian matrix. So let's actually go through a couple domains just to sort of get an idea of what we mean by better approximated or better represented. So let's assume that we have this two-dimensional plane, and let's assume that we want to cover all of quadrant 1. All right, so let's assume that we just want to cover quadrant 1. So how do I represent this in, let's say, rectangular coordinate systems? So we can represent this as the set of all xy in R2 such that x is greater than or equal to 0 and y is greater than or equal to 0. You might be thinking, oh, this is actually relatively easy geometry to work on because that is just a rectangle in the double integral world. But if I ask you represent this in polar coordinates per se, how would you represent it in polar coordinates? R theta, right? Again, let's assume that these are both real numbers. So in order to get this covered in the r theta world, obviously we would sweep with a bunch of arcs, right? So pretty much what we need is a radius going from 0 to infinity, and then we need to take each of these arcs and rotate them from 0 to pi over 2. So we can represent this in the polar world using 0 less than or equal to r less than or equal to infinity, and 0 less than or equal to theta less than or equal to pi over 2. So note that both of these geometries can both easily represent this particular domain D that we plan to integrate some multivariable function over. Obviously, we need not just focus on quadrant 1. We can expand this to, for example, quadrants 1 and also 2, 3, and 4. So how would I cover all of R2? All right, so D is equal to R2. So how would I represent that in the rectangular coordinate system? So that's xy in R2, such that x is a real number, y is a real number. Right, so notice that there are quite a few real numbers, in particular infinitely many squared real numbers to deal with in that particular coordinate system. But if we represent this in the r theta world, obviously rate r is still going to range from 0 to infinity. But there's one main difference here. Theta need only go from 0 to 2 pi. That is, it's going to be a closed and bounded domain. So 0 less than theta, less than 2 pi. You could also go from minus pi to pi if that, is a lot more easier to work with for you, because it's a symmetric interval, so sometimes integrals can simplify over that type of thing. Right? So notice that they're pretty much achieves the same exact goal. The only difference is this is an unbounded domain, this is unbounded domain, this is unbounded domain, but this is bounded. So if you have any problems, especially in the theory realm, where it's a little bit more nicer to deal with in the bounded domain, definitely polar coordinates definitely does have an advantage over this thing. But technically speaking, you can work in both rectangular and polar coordinates as long as the integral works in your favor. So let's look at another one just to make sure we get it. So let's assume that our region now, let's assume we have this curve y is equal to x, and this y. And let's assume that we want pretty much this infinite triangle. Let's assume that's D. So how would you represent this in rectangular coordinate systems? So that would be the set of all x, y in R2 such that x is greater than or equal to 0. So let's assume that that is going to be our independent variable. So when I pick my particular value of x, y is going to range from 0 up to x. So that means 0 less than or equal to y less than or equal to x for that particular picture. And if I want to represent this in polar coordinates, keep in mind that this angle here is going to be 45 degrees, aka pi over 4. So I can represent this as the set of all r theta in R2, such that, again, 0 less than or equal to r less than infinity, and 0 less than or equal to theta less than or equal to pi over 4. So what is the advantage and or disadvantage between the two? So notice that this is going to be a dependent domain, whereas both of these are independent domains. That is, I can do an integral with respect to r, integral with respect to theta, and technically I could interchange those limits as long as our function is well behaved. Right, so here we clearly see the advantage of how polar coordinates can work over this particular infinite triangular domain D, similar to how we had a bounded advantage, for example, if we want to sweep over R2. So we clearly see a few examples of sometimes it's easier to work in both rectangular and polar. Maybe it's easier to work in rectangular. Maybe it's easier to work in polar. So is it possible then to translate or transform your integral and your function into a new coordinate system? For example, maybe we want to convert from rectangular to the polar coordinate system, maybe we want to convert from the polar to the rectangular coordinate system, or maybe we just want to convert to a completely new coordinate system where, let's say, call it UV, where we know some transformational functions that go from one space to another. And that's what we're about to do. Let's bring back something that we did back in the world of linear algebra. Suppose I have a vector u and a vector v. My picture is drawing both vectors embedded in R2, but technically speaking, this can extend into Rn as well. Keep in mind, a vector is only uniquely prescribed a magnitude and a direction, not necessarily its endpoint or starting point. So technically speaking, this vector here is still v, and this vector here is still u, as long as they have the same exact magnitude and relative direction. So if I ask you, how can you find the area of the parallelogram spanned by these two vectors u and v within this vector space Rn? So you should know from the world of linear geometry, we can find this by doing the determinant of u1, u2, v1, v2, where u1, u2, v1, v2 are the vectors u and v. And a particular area is usually prescribed to be a positive number, so we take the absolute value of the determinant of that vector. Right? Now, why do I bring this up? Keep in mind, we're trying to take the area and transforming it into another. But this doesn't look like a rectangular coordinate system. It looks like maybe a parallelogram coordinate structure. So how can we possibly convert from one world to another? So what I want to do is suppose that G sends some domain D, subset of R2, and maps it to E, not that fancy E, but let's call it E, subset of R2 as well. So we're going to a subset of R2 to a different subset of R2 where one is going to be prescribed some particular geometry. For example, we're going to pick a point XY in this particular world D, and we're going to pick UV to be some particular point or coordinate system in E. So from the chain rule, how can we represent the differentials of x and the differentials of y with respect to the coordinate system of u and v, provided that the transformation itself is differentiable? So how will we do that? So that's going to be dx is equal to partial x partial u times the total differential of u plus the partial derivative of x with respect to v times the total differential of v. And similarly speaking, we could do it for y as well. So dy will be equal to partial y, partial u times du plus partial y partial v dv. So here are our two differentials, dx, dy, and we're trying to represent a new version of our area, which is going to be the product of these two differentials. So that means dA, which is going to be in the original form, dx dy, is going to be just found by doing the determinant of that pretty much vector spanned by those two differential vectors. So this is going to be equal to, by the same exact principle as before, the determinant of what? So first we're going to take this particular vector, which is going to span one direction, and then we're going to take this vector here, which is going to span another direction. So it's going to be equal to the determinant of xu times du, and then yu times du, and then we're going to have xv times dv, and then yv times dv. Right? So here we have this 2x2 determinant, and we can use our typical rules. So that's going to be equal to the absolute value of what? So it's going to be xu du yv dv. And keep in mind, x subscript u is the partial derivative of x with respect to u. And over here, we're going to have xv dv yu du. Notice that we have a couple common terms. We have a du dv, dv du, so we can factor that entire thing out. So we can represent this as the absolute value of xu yv minus xv yu times dx or du dv dv. But notice that this is just the determinant of another 2x2 matrix. So we can write this as the absolute value of the determinant of what? So this is just going to be equal to xu xv yu yv du dv, and this is the new representation of dx dy. So what is so special about this particular matrix? So this matrix here is known as the Jacobian matrix, and this right here is what we refer to as the determinant, or the Jacobian of the transformation g, where g sends xy to uv. Right? So therefore, we can write this in more theoretical form. So the Jacobian of g, transformation from xy to uv, is given by, let's call it jg, and this is defined to be equal to the determinant of xu xv yu yv. So therefore, this new coordinate system, dx dy, or the old coordinate system, I guess you could say, could be viewed as doing the absolute value of jg times the area in the new coordinate system, uv. Right? So now that we have the general structure in the theory form, let's actually do a practical example just to make sure you understand what we're actually doing here. Probably one of the most famous transformations of coordinate systems in the realm of two-domain dimensional calculus is polar coordinates. That is, we seek to transform xy, rectangular, some people also call it Cartesian, and transform it into the r theta world. So this is going to be our transformation g. So what is the connection between rectangular and polar coordinates? Let's just recall that. So x is going to be equal to r cosine theta, y is going to be equal to r sine theta, and x squared plus y squared, for which you can verify, will just be equal to r squared, since sine squared plus cosine squared is equal to 1. And also you can go backwards from polar to rectangular by doing theta is equal to the arctangent of y divided by x, and what would be the other one? So r will be equal to the square root of x squared plus y squared. Right, so this allows you to transform from r theta to xy, and this allows you to transform yx back to the r theta realm. All right, so let's see if we can derive the Jacobian of this transformation in the calculus form. So what do we have? So we're going to take the derivative of x with respect to r and the derivative of x with respect to theta, right? Because keep in mind, our Jacobian for g will be equal to the absolute value of the determinant of xr, x theta, yr, y theta. So pretty much r and theta are taking the space of u and v in the general form. So what is the derivative of x with respect to r? So x with respect to r, so cosine theta is just a constant. So that means this is just going to be equal to the derivative of r times the number, so that's just going to be a number. So this is going to be equal to the absolute value of the determinant of cosine theta. So what's the difference derivative of x with respect to theta? So that's going to be equal to minus r sine theta. Now let's do y. So the derivative of y with respect to r, that's still going to just be equal to sine of theta. And the derivative of y with respect to theta, that's just going to be equal to r cosine theta. Once we have our 2 by 2 matrix, then we just apply our AD minus BC relation for this determinant. So that's going to be equal to what? So that's going to be equal to cosine theta times r cosine theta, and then minus r sine theta times sine of theta. And then notice that we have a minus and a minus that turns into a plus, and notice we have an r and an r in both, so we can factor that r out. And taking the absolute value of r, that's just going to be equal to r, but usually we assume that r is greater than or equal to 0 anyway. So we're just going to be left with r times the absolute value of cosine squared theta plus sine squared theta, which we know is just going to be equal to 1. So we have that the absolute value of the Jacobian of the transformation from Cartesian to polar is just going to be equal to this factor r. So what does this mean from the integral perspective? So that means if we want to doubly integrate over some xy domain or some domain D traversed with the xy coordinate system of xy dx dy, then this would be equal to integration over D parametrized with respect to the r theta coordinate system. And then we're going to replace with x with r cosine theta, or we can just keep it as x and y. Maybe they things cancel, who knows. So r cosine theta, r sine theta, and then dx dy will be equal to the Jacobian times dr d theta. And we already derived the Jacobian to be equal to r, so we have dr d theta. So therefore, every time you want to go from rectangular to polar, you replace x and y with their corresponding polar representations and replace dx dy with r dr d theta. Right? Let's just do a quick example of how to work with this. So let's assume that D is the set of all points x and y in R2 such that x squared plus y squared is less than or equal to 4 and y is greater than or equal to 0. So what does this domain look like in the R2 world? So x squared plus y squared is equal to 4 is a circle of radius 2, and y greater than or equal to 0 just means we're working with the top half only. So that's going to be 2, so that's going to be minus 2. It's less than or equal to 4, so that means this right here is going to be our domain D. And let's assume that we want to integrate. So let's assume that f maps R2 to R with the functional relation fxy is equal to the square root of x squared plus y squared. So let's assume that we want to integrate this particular surface over this particular semicircular region D. So what would that integral be? So our volume will be equal to the double integral over D of the square root of x squared plus y squared dx dy. And then we're going to transform this into the polar coordinate system. So now we're going to go to polar. So what would that be? So let's do our r integral and then our theta integral first. So notice there that r is going to range from 0 to 2, and then theta is going to range from 0 to pi. Or you could go pi to 0, but that's going to go backwards. So this is going to be equal to r is going to range from 0 to 2, and theta is going to range from 0 to pi. Right, so that's going to be our two integrals. And then we're going to have the square root of x squared plus y squared is r squared by definition. And then we're going to have dx dy, which is going to be equal to r dr d theta. right? So that's what dx dy is. So what is this going to be? So notice that if we integrate with respect to theta, oh, my integral bounds are backwards. So that's r d theta dr, since I put my angular integral inside. Notice that there is no theta mentioned here. So that means the square root of r squared times r is just a constant as far as theta is concerned. So the integral of 1 with respect to theta is theta. Plug in pi, plug in 0, subtract, you just get pi. So this is just going to be equal to pi times the integral from 0 to 2. The square root of r squared is just r. Since we're working with the positives, only principal square roots apply here. And then r times r is r squared, so we're going to have r squared times dr. Now we're back into the calculus single variable integral style. So the integral of r squared is going to be equal to 1/3 r cubed. So we're going to have pi divided by 3 r cubed. And then r is going to range to 0 and also to 2. 2 cubed is equal to 8. So then we're going to have 8 pi divided by 3. Right? So that's going to be the volume of our surface over this domain D. Now, for fun and excitement, I recommend you even try doing this in the rectangular coordinate system. Slightly more annoying, not impossible, but compared to the polar coordinate system, polar coordinate is definitely the more easier route to go here. Before I get into the last example of today, I just want to briefly mention this particular theorem, which can come in handy for a variety of reasons. So what we have here is we have the double integral of the product of two functions fx and fy over some domain D, and we also have the absolute value here. And we're assuming that this double integral or this volume integral is finite. Usually when we say that this the integral of the absolute value of a function is finite, usually we say that that function or that function product is absolutely integrable. This idea of absolute integrability kind of goes back to our discussion of series, where we have that a series is, if a series is absolutely convergent, then it is also convergent as well, right? So pretty much what we have here is if we have an absolutely integrable function in R2, then what you can do for just the integral without the absolute values is decompose them into the product of two isolated marginal integrals, one with x only and one with y only. What's actually going on here is, well, as long as this integral is well behaved, x is a constant as far as y is concerned, so you can pretty much factor out everything, including the entire integral of x, and pretty much do the y thing first and then the x thing second. So that's pretty much what we have here on the right hand side, right? But it's not always true. It has to be satisfying the absolutely integrable property. So just keep that in mind. The proof of this is more for a real analysis world, so I'm not going to give it here, right? But we'll come back to it later if we need to. So with this idea, what I want to do is use it together with our polar coordinate transformation to find the value of I is equal to the integral from minus infinity to infinity of e to the minus x squared dx, which is probably one of the more famous integrals in the realm of single variable calculus and also multivariable calculus once you have polar coordinate systems, because it has so many applications. So if I is equal to this, then what we can do is we can square this particular integral. So we can write this as the integral from minus infinity to infinity of e to the minus x squared dx, and multiply it by itself. Again, the integral from minus infinity to infinity of e to the minus x squared dx. Now notice I didn't write x for the second integral, I wrote y, because keep in mind this is just a number, so regardless of the letter you put in the variable, it should be equal to the same exact number. So by the theorem I just mentioned, you should be able to verify that if I take the absolute value of these two functions multiplied, then the integral will indeed be finite. So I can actually write this as the double integral all over R2 of e to the power minus 1/2, or just minus x squared plus y squared dA. So that's the value of I squared. You might be thinking, why did I do that? Well, do you know the value of I in this particular case? No. But when I multiply it by itself, provided it exists, I get this particular integral here, which reminisces of a polar integral. So what can I do here? So if I convert this to polar coordinates, what am I going to get? So this is going to be equal to, so how do I span across R2? Well, I need to send R from 0 to infinity, and I need to send theta from 0 to 2 pi, and then I'm going to have e to the minus r squared, since x squared plus y squared equals r squared, and dx dy is just going to, again, be equal to r dr d theta. And again, I wrote my theta integral on the inside, so that's r d theta dr. Right? So that's going to give us this particular relation. Again, notice that I do not have any thetas here, so I can integrate from 0 to 2 pi, and then I'm going to get 2 pi as my constant. So I'm going to have I squared will be equal to 2 pi times the integral from 0 to infinity of e to the minus r squared r dr. Now I have a single variable integral, so I can use u substitution to solve this. You might want to pause this video and see if you can do this on your own. So let u be equal to minus r squared. When u is equal to minus r squared, du will be equal to minus 2r dr, forcing dr to be equal to du all over minus 2r. Also notice that when r belongs to 0 to infinity, u will belong to 0 to minus infinity in that direction, so make sure you do not get them backwards. So we're going to have 2 pi times the integral from 0 to minus infinity of r e to the u, and then we're going to have du all over minus 2r as our differential of r. A few things cancel here, which is actually pretty nice. Our 2's will cancel, my r's will cancel, and my minus sign can revert my boundaries for my integral. So I can write this as the integral from minus infinity to 0 of e to the u du, which should be nice. So we're going to have u goes to 0, u goes to minus infinity. So that's going to be equal to, and where's my pi? Let's not forget our lonely little pi, that matters here. So e to the 0 will be equal to 1. E to the minus infinity will be equal to 0. So we're just going to be left with pi. But keep in mind, this is the integral I squared. So that means I will be equal to the square root of that, which is equal to the square root of pi. Right? So with that, then we can conclude that the integral from minus infinity to infinity of e to the minus x squared dx will just be equal to the square root of pi. Isn't that a beautiful integral? Now there's one more other infamous integral that I do want to mention, and it follows the following theorem. And if you've done any probability or statistics, this theorem should look very familiar. Let's assume that mu is any real number, and let's assume that sigma squared is any positive number. Then you should be able to verify, using some substitutions, that the integral from minus infinity to infinity of 1 over sigma square root of 2 pi times e to the minus 1/2 x minus mu over sigma of the quantity squared dx will be equal to just 1. And if you know any probability, you should know the significance of this 1, because if you know from single variable calculus, if this function is always positive and the integral turns out to 1, then what we have here is a probability density function. In particular, this is what we call the normal probability density function, but the applications of that pretty much follow the same exact thing as before. Anyway, that's just an introduction to the realm of Jacobian matrices and transformational coordinates from the perspective of multivariable calculus. Hope you enjoyed this video, and I'll see you in the next one. Take care.